Hi guys, this video describes a C++ class that can be used to implement a binary search tree and a corresponding class that can implement a binary search tree node. This is going to be the foundation that we use to define code for the map and binary search tree operations that we'll implement in some later videos. We're going to start with a class for a binary node. That's the building block of binary search trees in the same way that linked list nodes are the building blocks of linked lists. So you need the node class before you can make the tree class. To review, a binary node has a pair storing a key and a value. We're using these trees to represent the map abstract data type. So every entry into the data structure is a pair that associates a key with a value. In this sketch, the keys are integers, 37, 61, and so on, and there's a convention that when we sketch a binary search tree, we don't bother drawing the values because it would clutter things up too much and take too long. Every node, in addition to that pair, has a left child pointer, and we depict those as going downward to a lower level in the tree. So for example, 61's left child is the 55 node. Every node also has a right child pointer that we depict as going downward, so 61's right child is 83. And every node has a parent pointer that we draw upwards, so 61's parent is 37, and 83's parent is 61. And these pointers can be null when there's nothing there. So 37 is the root node, it's at the top of the tree, it has no parent, so 37's parent node would be null. 55 is a leaf node. At the bottom of the tree, it has no children, so 55's left pointer and 55's right pointer are both null, and the same is true of 83, which is another leaf node. Finally, we use the word edge sometimes to talk about the two parallel pointers going back and forth between a parent and a child node. So 61's left child pointer points at 55, and vice versa, 55's parent pointer points back up at 61. We use the word edge to talk about those two pointers that go back and forth in the same direction between the same two nodes. Let's get into the code for a node. So it's a fairly simple container class, meaning that it contains a few data members and has accessors and mutators for that, and that's pretty much all it does. It doesn't have any other complicated operations. There are the three node pointers, of course. So as sketched here, every node has a parent going up, a left going left and down, and a right going right and down, and we see that there are three standard shared pointers to other BSTNode objects called parent, left, and right. In addition, every node has contents, and the contents is a key comma value pair, and we're using the std pair standard pair data type that stores a key and a value. Note that BSTNode has to be a template class with two template parameters. In the past, all of our template classes have had one template parameter t for the data type of one element, but now that we're dealing with a map, we have two template parameters. Capital K is the data type of a key, and capital V is the data type of a value. Keys have to be comparable data types. They're usually integer types like int or string, and V can be pretty much any data type. Note the order of the constructor. Just like with the linked lists, I try to organize the order of the constructor to be the same way that we read off in English text reading. So when we read in English, we go left to right and then to the next row, left to right. In the sketch here, the top thing is the parent pointer, and then the next row goes left pointer, the contents, and the right pointer. So that's the reason why the arguments to the constructor are organized first parent, then left, then contents, then right. In addition, there's a dot 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 here, an ellipsis, just for space. I did not put in all of the accessors and mutators, but there would be accessor functions that return all four data members, the three pointers and the contents, and mutators to set them. In addition, we would probably have a convenience function that returns the key. The key is always the pair's first element. So contents.first is called the key of the node, and the value is stored in contents' second element. Now let's get to code for the overall tree. So an entire tree, of course, probably has numerous nodes in it, and the entry point into all of those nodes is the root pointer. So a binary search tree has a root pointer, which points at the topmost binary node, so the class from the previous slide, and a tree could be empty. In that case, the root pointer would be null. We also have an integer size so that we can return the size of the tree in constant time. And we visualize a binary search tree in this kind of tree shape, as we've been showing in the sketches. Here's how we would code this up in C++. Again, it's a template class with a template parameter k for the key type and a template parameter v for the value data type. There are only two data members. It's a pretty simple class in terms of the data members. There's a node pointer to a root. So that would be a standard shared pointer to a BST node with the same key value data types called root underscore. And also the integer size that counts how many pairs are in the tree. And I guess note the constructor argument order. The default constructor doesn't need any arguments at all. It just sets up the tree as empty. So by default, the tree is empty. So root points at null and the size is 0. Okay. What we're going to launch into next is defining the map operations in the binary search tree using this node structure. Let's recap what those would look like in code. We defined these as pseudocode operations in a previous video. Now we're defining how the actual function input-output types would look. So there are 4 major operations in a map. The first is called contains, and this is kind of a query that asks, does the map or the tree contain a given key? So contains is passed a key k object called query. So it's a constant reference to a k, meaning a key type, again, probably an integer or a string, and returns true if the tree contains that key and false if it does not. We have an operation to actually get the whole pair out of the tree. So that's called find, and it's given the same data type, a constant reference to a k, a key, and that returns the pair that has the matching key. But if that can't be found, this function throws a range error exception. So the idea of find is you use this when you're pretty sure that the given key is actually in the tree. If you're unsure and you want to learn about whether a key is in there, the contains function is more convenient for that because contains does not throw exceptions. And then to add a pair to the tree, there's this insert function. Insert takes a reference to a pair. The 2 ampersands make this an R-value reference, which is a C++ technicality, but basically it's given a key value pair that should go into the tree. And the idea of insert is that you only call this when you really do want to put that pair in there. So assuming that the tree does not already have a pair with a given key, that pair is placed into the tree and the function returns true. But if there's a duplicate key already in the map, this function does nothing, it has no effect, and it returns false. Finally, there's erase to take a key out of the tree, and like insert, the spirit of erase is that you are using it when you really do know that there's a key in there that should be removed. So you give it a reference to a k, a key type, as an argument, and the erase function takes out the pair with the associated key and returns true, and that can be done. But if the given key is not actually present, the function has no effect, and it returns false.